Okay, great. Thank you all for joining us. It's my honor to introduce this week's colloquium speaker. We have with us today Silvia Galli from Paris. So Silvia got her PhD just in 2011 from La Sapienza, Rome, and APC in Paris. And her initial PhD work bore a lot of the hallmarks that you'll see in her work that she's describing today. She was using CMB to unpack all kinds of new phenomenology that she was teaching us in the field we could learn from CMB. Her early work included using CMB to constrain reionization history, dark matter early annihilation, how to combine CMB data with BBN to constrain exotic fundamental physics like evolution of gravity, or how to combine cluster SE data with X-ray follow-ups to constrain the evolution of the fine structure constant, as well as constraining the whole gamut of cosmological parameters that are now familiar to us as goals of the next round of CMB experiments, but that were not so familiar to us at the time, like the constraints on neutrino mass or the number of effective species that we can expect out of the next generation polarization experiments. After her PhD, Silvia spent 3 years or so as a postdoc at IAP in Paris, and then came across the pond, spent about a year in Chicago before she was lured back to a permanent scientist position at IAP. And in that time, she's had a huge impact on the analysis of the Planck data set. She's made contributions to the delivery and fundamentally the testing of the Planck likelihood that we've all relied on for so much of our current cosmological results. A thing that I really appreciate about Silvia's work is not only does what she's done reflect a deep understanding of the fundamental physics that's being constrained by these data sets, but also a deep understanding of the fundamental uncertainties that real data carries with it. And so every time we listen to Silvia and she tells us about what we should and shouldn't believe in the likelihood results that we've seen, I learned something new. So I'm eager to hear what she has to say about results from Planck. Please join me in welcoming Silvia.
So, hello everybody. Thank you very much for this amazing introduction. Thank you, Don. It's a great pleasure to be here today, back to Harvard. I already had such amazing discussions in these 2 days. It's really a pleasure to be here. Today I'm going to talk about cosmology from the Planck satellite. Last year I co-led the work that we've done in the collaboration to publish basically the paper describing the cosmological results from Planck, in particular on cosmological parameters. And I will mention some of the work that we've done to ensure that these results are actually true and robust, which is contained in the likelihood paper that we published this year after many years of work. And clearly the Planck collaboration have published a lot of different results between last year and this year. These are the legacy results, but I will mainly focus on these 2 papers. And before starting, clearly I'm here on behalf of this big collaboration. You have for sure seen this slide many times, but it's really, it has been an amazing group effort of many brilliant people that have put their work in this collaboration. So I know this is a broad audience, so I thought that I will start with a small introduction about the cosmic microwave background and why we are interested in observing this radiation from early times with Planck and other experiments. So you know that the cosmic microwave background comes from a redshift of around 1100 from the last scattering surface when the universe was about 3000 Kelvin. And what's so special about this epoch is that before then the universe was essentially completely ionized, and there were interactions, Thomson scattering between electrons and photons that were so efficient that the universe was essentially opaque to photons. Photons could travel very short distances. And what's special about the epoch of recombination, and then which produces the last scattering surface, is the fact that when the universe cools down at a temperature of 3000 Kelvin due to its expansion, protons and electrons recombine in neutral hydrogens, and photons are finally free to propagate through the universe till us. Now, the very interesting thing about this radiation is that it encodes a lot of information about the whole history of the universe, starting from the initial conditions, from inflation, the small seeds in the matter density, the small perturbations in the matter density that then led to the formation of the structure that we know today in the universe. It encodes, the CMB also encodes information about the photobaryonic fluid before recombination, in particular the acoustic oscillations that were set in the fluid. But it also tells us something about what happened later, in particular, for example, about the epoch of reionization at around redshift of 7.8, when first stars start to reionize the universe, freeing again the electrons, and this produces scatters with the CMB photons, and the signature of which we see in the CMB anisotropies. And also the photons get the effect of weak gravitational lensing from the large-scale structure of the universe. So we get this amazing information really from the first instance of our universe till today. And so what we observe, so the universe, the CMB is on average has a black body spectrum, which on average has a temperature of about 2.7 Kelvin. So this is the monopole, which we don't observe with Planck, but was observed, for example, with the COBE satellite. If you remove that, and you remove also the dipole due to the motion of the sun with respect to the CMB frame, you get to observe anisotropies in the temperature of the CMB, so basically cold and hot spots in the sky. These temperature fluctuations are at the order of 10 to the minus 5, so they are very small compared to the monopole, which is 3 Kelvin. This is a Gaussian random field. So we actually, since this is a Gaussian field, all of the cosmological information you are interested in is contained essentially in the two-point correlation function, or more properly for CMB studies, in the power spectrum in spherical harmonic space. What it means is that if you have a map like this, with different temperature different temperature anisotropies in different directions, you can decompose these in spherical harmonics. This is nothing else than a Fourier transform, just on a sphere rather than in 3D. And then you have these coefficients that are containing all the cosmological information, and you take the variance. Basically, you estimate the variance of these coefficients, which are these C of L's that contain the information about cosmology. So all of these nice things I told you about, information of the primordial power spectrum set by, for example, inflation, the density of dark matter and variance that govern much of the physics going on at early but also at late times, and so on and so forth. So the power spectra that you see all the time from CMB is nothing else than these CLs. What you see every time is rather CL multiplied by L plus 1, for reasons I'm not going into, but essentially that's what I'm going to use and show you in the rest of this talk. So the important information is that essentially this is the two-point correlation function in spherical harmonic space of this Gaussian random field. Now, the interesting thing about the CMB is it's that we can study these temperature fluctuations, but we can also study its polarization. The CMB is polarized because of Thomson scattering and the fact that we have sources of quadrupoles in the early universe. So quadrupole anisotropy means just that an electron will see more energetic radiation coming from one direction compared to another. So in a classical way of viewing this, the electron will oscillate in a preferential direction, and this will give you polarization of the CMB. And there are these quadrupoles in the early universe sourced by scalar perturbations. So in other words, just these underdensities and overdensities of matter that we see in the early universe, which creates gradients of velocity that gives you some level of quadrupolar anisotropies around these electrons. And this kind of sources produce what we call E-modes, which are these kind of patterns, which are parity invariant. But the cool thing is that also tensor modes, so this means, for example, primordial gravitational waves produced by inflation can produce these quadrupolar anisotropies, and these are and they produce both B modes and E modes, and B modes have these kind of patterns. And you can create exactly as for temperature with slightly more math. You can also calculate the power spectra of polarization and also of the cross correlation between temperature and polarization. And what I'm showing you here, this is the power spectrum of temperature here. This is the power spectrum for polarization, and you can see that the level of polarization for the CMB, the amplitude is lower. The power spectrum level is about 100 times smaller. At the math level is about 10 times smaller, clearly. And this is the spectrum of B modes that we haven't observed yet. We haven't detected gravitational waves from inflation. Clearly, this is the holy grail of our field right now to try to detect this signal, whose amplitude is unknown. But we also have some B modes that are created by late time effects, in particular gravitational lensing, that can mix E modes into B modes by distorting essentially this pattern into this one. Something that, so in this talk I will not talk about B modes because Planck was not designed to observe this signal, but rather I will focus on temperature and polarization and on the cross correlation, E mode polarization and the cross correlation between the two. But here I want you to focus on this bump here in the E modes. This is at large scales. So again, this is the power spectrum as a function of multiples. So this is small scales and this is large scales, where L of 200 is about 1 degree in the sky. And this peak here is due to the reionization of the universe when the CMB photons rescatter at redshift of around 7.8. And it is important because it allows us to set constraints on reionization, on the optical depth to reionization. It's important because this reionization has an impact also at smaller scales, but it's degenerate with other parameters. And so observing this bump is important for CMB studies because it allows you to measure reionization and break degeneracies with other parameters that affect the rest of the power spectra. And I will show you what we've done in Planck to constrain this. So what is Planck? Planck is an ESA satellite. It was the third generation of full sky missions observing the sky. It operated between 2009 and 2013, so it's a long time that the satellite is not taking data anymore, but it took a long time to have the analysis, the data analysis right. And it had on board two instruments, the low frequency, LFI, and the high frequency, HFI, covering a large range of frequencies from 30 to 857 gigahertz, with 7 of these bands sensitive to polarization. And the reason why we need so many frequency bands in CMB studies is that we want to disentangle the emission from CMB, which has a black body spectrum, from astrophysical sources, both galactic or extragalactic. And so having so many frequencies allows us to disentangle the different emissions. And we had our first data release and results in 2013 based on nominal emission. So this was about the first 1 year of data. And for the results, we used temperature only. Polarization was so tricky that it took us much longer to use for the first time. So in 2013, we only published results based on temperature. And we used WMAP at large scales in polarization to constrain the optical depth to reionization. In 2015, we used full mission, which means a couple of years of data for HFI and even more for LFI. For the first time, we used the polarization at small scales from Planck, from HFI. And also at large scales, we constrained the optical depth to reionization using LFI. LFI is less constraining than HFI, and at the epoch, however, the systematics in HFI did not allow us to use this very, very powerful data set. And then what happened between 2015 and 2018, and actually I would say 2019, because as I said, the likelihood paper was out just a couple of months ago, sorry. It's really that we worked on this data set for 4 years to try to clean this as much as we could from systematics, in particular in polarization. We felt in some way we felt the responsibility to give to the community the best data set we could as a legacy. And this took a lot of time to make sure that we understood the effects in the data. And this had very good results, I would say. It was a lot of work, but it allowed us to use the HFI data to constrain reionization. So now we use large-scale polarization from HFI to do so. And we also improved the systematics in polarization at small scales. And in the next slide, I want to give you a sense. So later, this talk will be more about the science, but I just want to give you a sense of what we fought against in these last years. And this is common to many different experiments in CMB, and some of these problems will be a problem for future for other experiments as well. So in Planck in particular, our detectors are sensitive. Our polarized detectors are that are sensitive to one particular polarized direction. Measure a combination of intensity and of the Q and U Stokes parameter that tells you about polarization. And so if you want to just measure Q and U and eliminate the signal from intensity, what you can do is that you take two detectors with two different polarization directions, and you just subtract one from the other. If this is perfect, you will eliminate the signal from intensity, and you will be left only with polarization. But you can very easily imagine that if, when you do this differencing, you have you don't know very well your detectors, meaning you have differences in the calibration, you have differences in your beams, you have differences in many different things that can go wrong in your detectors. You might confuse intensity for polarization, or in other words, you can have leakage from intensity to polarization. And since the temperature of the CMB, the intensity of the CMB is at the map level is more than 10 times bigger than polarization, even small errors in your knowledge of the detectors will end up in leakage from temperature to polarization. And so this was solved in Planck in many different ways. We had different effects that could give leakage. We had improvements in the way we do maps. We have something that really helped was having end-to-end simulations, so simulating the instrument from, really the time order data till the cosmology, and this allowed us to understand a lot of these effects. But this is really understanding the sources of this leakage was one of the big things that happened in the last 4 years. And the second one is that some of our detectors, so our polarized detectors, are not 100% sensitive to polarization. You throw to them polarized light, they're going to absorb, say, 85% of that. So you measure this on the ground, and you have an uncertainty, or we had an uncertainty, which was sub%. And then in flight, we discovered that probably these uncertainties were estimated by a factor of 5. So the uncertainties that we had in flight were, so the differences that we were seeing from detector to detector of these polarization efficiencies were 5 times larger than what we thought. It took like 1 year to understand that this was the problem, to convince ourselves that yes, maybe something went wrong. So it takes huge amounts of time just to understand what's going on in data. And we found a way to correct for this, but this took some time. And clearly, we are very honest about the limitation of these data. So it's when you have systematics like that, we say, we have different pipelines treating these systematics in different ways, and we think that we understand these effects at the level on cosmological parameters at the level of 0.5 sigma. So this is our estimate, say, of our systematic uncertainties. End of the more technical part, but just to give you a sense of of why it took so long to get the data right. So these are the beautiful power spectra from Planck that we use for science. This is the temperature power spectrum that didn't change a lot since the second data release. We did changes, more checks, but things didn't change much. This is the cross-correlation between temperature and polarization, and at small scales, this improved a lot because we corrected for temperature to polarization leakages due to uncertainties in the knowledge of our beams. And this is the EE power spectrum, and this one improved a lot rather because we now have a better understanding of our polarization efficiencies, which is not completely settled yet, however. And at large scales, as I say, for the first time, you can really see the bump from reionization using the HFI data. One question that I get a lot every time is why there is such large error bars here, and then abruptly they are small. It's just because I'm just changing the scale here. But since a few people asked me this in different talks, I'm just, this is just a change of scale between these two regimes. And the reason why we actually use L of 30 as a shift is that actually we have two different likelihood codes, so codes that we used for the cosmological analysis in these two regimes, because the statistics of these points are different from this one, so we use different approximations, and the division is, or the cut is at L of 30. And one other thing, so the baseline Planck results come from the 3 power spectra, but also from the lensing potential power spectrum. So this is really the effect of gravitational lensing that we measure on through the non-Gaussian signal that gravitational lensing leaves in the CMB maps, in particular from the 4-point correlation function. And this is one of the best measurements, actually the best measurement and the only one on the full sky of the lensing potential. And this is included in all of this, when we estimate cosmological parameters. So we use this beautiful data set to constrain cosmological parameters, and I'm going to start with our beloved lambda CDM model. So you know that this model is a model based on validity of general relativity to describe gravity, standard model of particles to describe interactions between particles, and so on. And with only 6 cosmological parameters, it allows us to, or it's able to fit a lot of different observables. And in particular, we have 2 parameters, the scalar amplitude of the primordial spectrum and the scalar spectral index, which model the initial conditions, so the primordial, the power spectrum We have one parameter which is linked to, say, this is the angular scale of sound horizon. So it's the typical angular feature is the angular dimension of the sound horizon at the epoch of recombination. And this is equivalent of using, you could use here the density of dark energy, or you could instead using also the Hubble constant as a parameter. It's a parameter that tells you how far is the last scattering surface, essentially. We have one parameter that is the optical depth to reionization that I already mentioned, and two parameters that govern the density of baryons and dark matter in the early universe. And all of these effects have a different impact on the cosmological parameters. And plus, we have some assumptions that when we have fun with extensions of lambda CDM, we can also explore and see whether they are compatible with our baseline assumptions. And so the results for this model are summarized in this table. Clearly, I don't want you to read into these numbers. I just want to highlight a few points. So what you're seeing here are the 6 lambda CDM parameters and the 3 derived parameters, the Hubble constant, matter density, and matter perturbation amplitude. This is the mean. This is the uncertainty at 1 sigma, and this is the percent accuracy on each of these parameters. And the first thing that I want to underline is the fact that we really entered this era of precision cosmology. We measure most of these parameters at the sub-percent level. This is true, but for the reionization optical depth that we measure at with a precision of about a bit more than 10%. And this is because it is so hard to get these measurements at large scales in polarization, and the constraint is coming essentially from that. But the others are sub-percent, and in particular, the acoustic scale of sound horizon is measured at the level of 0.03%. And the reason for that is that Planck observes multiples from 2 to 2,500, and this means that we observe a lot of the peaks and troughs of the CMB. And basically, this parameter tells you the spacing between these different peaks. So if you observe a lot of peaks, it means that you have a very good constraint on this parameter. We observe 7 peaks in temperature, 6 in the cross-correlation between temperature and polarization, and 5 in the EE polarization. And this gets us to this very low number. The other thing that I want to stress is, so I already talked about acoustic scale, the reionization optical depth. I'm going to talk little bit more about this in a couple of slides. The scalar spectral index is now measured to be different from 1 at 8 sigma. This is important for inflation. This is an important prediction of inflation, that it should be smaller than 1, so not perfectly scale invariant. And we check that in any extension of lambda CDM that we tried, this is true at least the 3 sigma level. And we have the best measurement of the Hubble constant. 67.4 plus minus 0.5. This is a 0.8% measurement of the Hubble constant. Now, you might have heard that for some people, this is too low. And this is probably one of the most exciting things that are in cosmology right now. I will talk a little bit more about this. But just to underline something that probably you already know, the CMB doesn't allow you to measure directly the expansion rate of the universe today. You need a model in order to predict the expansion rate of the universe today. So this is the Hubble constant assuming lambda CDM. If you change the model, and it's not easy to change the model in order to fit, for example, or to have a better agreement with direct measurements and not screw up all the other information that we have about the universe. It's very hard to do, but potentially you can change the model in order to change what you get from CMB about the Hubble constant. And let me say that, as I said, the systematics that we have in polarization do not change this number by more than half a sigma, mainly on the baryon density. For example, the Hubble constant is stable if you do different things for the systematics. So this is just to show you that although we had all of this, work going into understanding better systematics and so on, the scientific conclusions from Planck have been stable since 2013. Although the statistical power has increased during the years, our conclusions did not change. So these are the cosmological parameters, again, with these two being the derived parameters, Hubble constant and sigma 8. The big changes are due essentially to the change in the estimate of the optical depth to reionization, just due to the fact that in 2015 we used less constraining data from LFI, and now we have more constraining data from HFI, and these shifts are in statistical agreement. And all of the other small shifts at the level of 0.2, 0.5 sigma, and so on, are due to these corrections in systematics that we understand extremely well. So what about a little bit more about the optical depth to reionization? So now we measure tau to be around 0.05, which corresponds to a redshift of 7.6. And this is in agreement with what we measured, as I said, in 2015 from LFI, where we had a slightly higher tau, but with a much larger error bar, almost 3 times larger. And this is the results that we get from Planck gets or give you a tau which is lower, and therefore a redshift of reionization which is lower than what WMAP9 used to have. And we think we understand this difference. So WMAP did not have high frequency information, such as Planck have. And this high frequency information, in particular from the 353 from gigahertz from Planck, is useful because it allows you to really have a good handle on galactic dust. And we think, so if you use this 353 to clean the WMAP maps, we get reionization optical depth, which is in much better agreement with Planck. So we think that what was going on is that there might be, or there could be residuals, dust residuals in WMAP that could have led a higher reionization optical depth compared to what we get in Planck. And the second thing I want to say about reionization is that when you estimate these numbers, clearly you assume some sort of some sort of reionization history of how the free electron fraction evolved with redshift. And what we tried is to try to open up and relax this model, and we get results that are consistent with just the baseline model that we usually use. And I'm going to say this, there was a claim using LFI data that there might be reionization already at redshift earlier than 15, but with the new data set, we don't find any of that. So probably these early claims were just statistical fluctuations. So the lambda CDM model fits extremely well the Planck data. And then you can do clearly consistency tests with other probes, such as baryon acoustic oscillation, redshift space distortions, high redshift supernovae, and one of my favorite ones is measurements of deuterium and helium combined with BBN calculations that allows you, for example, to calculate omega B, so the baryon density from BBN and primordial elements, which agree extremely well with the baryon density that you measure from CMB. This is telling you that we understand physics over a crazy number of orders of magnitude in the history of the universe. This is, I think, one of the most shocking thing of the whole thing. Like that these two numbers coincide, I think it's amazing. But we have good consistency in the lambda CDM model for these different things. But as you very well know, we have this huge difference now between what we get from CMB, Planck in particular, but you get the same results also if you combine, for example, WMAP plus ACT and SPT, so small-scale ground-based experiments plus baryon acoustic oscillations. Or you get the same number that we get from CMB if you combine baryon acoustic oscillations plus either weak lensing from DES, for example, but also could be high redshift supernovae, and measurements of BBN. You need the combination of these three because baryon acoustic oscillations are essentially sensitive to there is a degeneracy between omega matter and H naught, and you also need the density of baryons in order to calculate the dimension of the sound horizon, and therefore know the physical dimension of the baryon acoustic oscillation feature. And to constrain these things, so omega m and H naught, if you get baryon acoustic oscillations measurements at different redshifts, the degeneracy between these two parameters change, and so you are able to disentangle between the two by having a lot of redshift information. And this is further broken by having some other data set, for example, weak gravitational lensing that gives you constraints on omega m. And then you need something to give you this, the baryon density, and this is given by BBN. And this leads to H naught, which is low, so amazingly the same exact number as Planck. Well, for this particular combination, but as I said, people tried, instead of these, putting supernovae and so on, but it's around this value with an error bar which is about twice as Planck. And this is in strong disagreement with, first of all, what we get from supernovae. So these are relatively low redshift supernovae at redshifts, I think, below 0.15, I think, whose absolute magnitude is calibrated with local measurements of Cepheids. And this gives you 74 plus minus 1.4. This is Adam Rees' group, and Adam is basically publishing one paper every 2 months. So like keeping up like with the exact number, latest. This is not latest. This is Rees 2019, but there is another paper that came out in August with the new mega maser measurement, and it's like now, yeah, like 73.5. But anyway, this is roughly the number. And this is in agreement with what you get from measuring time delays from multiply imaged quasars. So these are quasars that are strongly lensed and have multiple images, and you can basically observe features in these light curves and measure basically the time delays between one and the other because they follow different light path while strongly lensed. And this gives you information about H naught, and in particular they get 73.3 with slightly larger error bars. And then if you combine these two, you get this number here, which is in 5 sigma disagreement with Planck now. So for the particle physicist people, we have 5 sigma. So we're getting serious here. I personally get excited with 2 sigma. So this is like, whoa, but this is overwhelming. I spent years of my life trying to understand 0.3 sigma differences on stuff. So anyway, life in Planck. Anyway, so how do you reconcile these two measurements? This has been with us since the first release of Planck in 2013. At the epoch was a 2.5 sigma difference, and at the epoch we started this amazing fight, between two groups, with the supernovae group saying you have systematics in your data, and then they were replying back that we had systematics in our data. And this was very, very healthy because it triggered a lot of checks on the different data sets. And all this year, we really spent a lot of time in trying to understand whether there was something wrong in the data sets. And what's really cool about today is that now we have 2 measurements here and 2 measurements here that are independent and are telling you 2 different stories. Now, what's common about these 2 measurements here is that they are not direct measurements. They are based on the same lambda CDM model. So if the model is wrong and there is new physics that we haven't included in our model, we might be able to push these measurements to be in agreement with direct measurements. So this is clearly the most exciting hypothesis, and I will show you a few ways of how people are thinking of solving this. For the moment, there's no good solution to this. It's very hard to do properly. Clearly, so it starts to be really hard that this is a statistical fluctuation at 5 sigma. It might be systematics, but if it's systematics, then it's either in both of these or in both of these. Might be, we keep checking, but this is the big open question, I think, that we have right now. So if this is really new physics, how do we solve this? Well, people have tried to do crazy stuff with the late time evolution of the universe, with dark energy, dynamical dark energy models, or decaying dark matter, interacting dark matter, dark energy, and so on. And the problem with that is that we have a lot of data in the late universe. So these models are highly constrained by BAO and supernovae, high redshift supernovae, and so on. And there is a growing consensus in the community that maybe we need to change the early time physics, and in particular, the way we calculate the physical scale of the sound horizon. So basically, the CMB and the BAO measure these angles in the sky, and to convert that into distances, you need to know this RS, this sound horizon scale. And if you change the model, you can change the calculation to get that. How do you change that? Well, there are different ways, but every time you put an ingredient to change that, you're screwing up something else, and that's why it's so hard. So one thing that people thought about immediately is, we have extra degrees of freedom. We have number of relativistic species, which is usually 3.046 if you assume a standard thermal history of the universe and 3 neutrinos. You might have more radiation, and why more radiation in the early universe works is because if you have more radiation, you're changing the expansion history of the universe at early times, and so this has an impact in the way you calculate this RS scale. The problem is that this cannot be the solution, because while there is a strong degeneracy between the number of relativistic species and H naught, if you consider only scales of the CMB, which are up to L of 1,000, as soon as you observe the damping tail, basically you have, this gives you an extra constraint on NF, which doesn't allow you to go very far from the lambda CDM value. So essentially, if you use NF, you go from 4-point-something sigma, which is the difference between Planck and the Schu's value, to 3 sigma. So you solve some of that, but that's not the full story. Then people tried to avoid these constraints coming from the damping tail, doing something really fine-tuned by changing the expansion history of the universe very early, at very early times, at redshifts. I think the peak was at the L of 3,000, around the matter radiation equality. These are early dark energy models. Also, this helps you to get a couple of sigma of this difference, but don't go all the way, and are extremely fine-tuned, and you add a lot of parameters to do this. Neutrino strong interactions. So you add one neutrino, and then you assume that there are strong interactions between them. Cute idea, probably already ruled out by laboratory experiments. We know that neutrinos do not strongly interact with each other. But it's all these models, people were trying things, and it's cool because you understand which are the knobs that you can play with to solve for this, although these are clearly still toy models and they don't pretend to be the truth. And another idea that came out also a few months ago was to have modified gravity that would actually change the period luminosity relation of Cepheids from what you measure in the Milky Way, for example, from the ones that are used in the second rank of the distant ladder to actually measure H0 from supernovae. But this kind of also the models I think do not work to solve tension then with the time delays measurements. So the overall, I think, conclusion from this is that right now there's no good solution. There's a lot of creativity, and people are really thinking hard about good models to solve this, but so far we don't have a conclusive model that actually can explain this difference. Now, another difference that you might have heard of is on sigma 8, or more, what I'm showing you here is S8, which is a combination of these sigma 8 parameters, so basically the amplitude of matter perturbations today within a radius of 8 megaparsec, multiplied by omega m, the square root of omega m, as a function of end omega matter. And there is this difference between weak lensing measurements such as KIDS or DES and Planck, and this is in particular from a paper from Judaki et al., which combined actually the data from DES and KIDS. And this difference is at the level of 2.6 sigma. Now, this is something that, also started with cluster of galaxies counts a while ago. They also claimed that sigma 8 was lower from those measurements compared to the CMB from Planck. This is at the level of a couple of sigma. Whether there are systematics in these measurements that can reconcile this, or in Planck, or there is something more interesting going on. This time will tell. I think we need more data to assess whether this is robust or not. So I want to mention what in the collaboration, we started calling curiosities. So the history of this name was that we didn't really know how to call stuff in our consistency tests that were consistency tests that were failing at the 2 sigma level. So this is not a problem. A problem is 3, 4 sigma. Still, you want to make sure that you checked and you looked at this stuff carefully. So we started calling them curiosities. There are 2 in the data that are at the level of a couple of sigma or a little bit more. This A-lens parameter, which I'm going to talk about now, and the fact that if you use the low L's from Planck, say from 2 to 800, you get a cosmology which is slightly different from what you get from L of 800 to all the way. And when I say they are different, they are statistically in agreement at a couple of sigma level. But whether, this is telling you that there are systematics or not, clearly we looked at this very closely. But again, they are statistically compatible at the 2 sigma level. But for those of you who know a little bit about these things, these 2 problems are exactly the same problem. It's just a different way of looking at the same features in the power spectrum, and they are picked up just either with one extra parameter, which is this A-lens parameter that I'm going to talk about now, or by fitting separately the 2 chunks with lambda CDM model, but just separating the 2. And if you want to talk about this, I worked on this for years, so I'm very happy to talk more, but it's very technical, so yeah. So what is a lens? So I already told you that the effect of gravitational lensing on the CMB, so there is this effect of, say, mixing E modes into B modes that I showed you at the beginning of the talk, but that effect is not important here. What's important is that it has an effect on the power spectra, both in temperature and polarization, by smoothing the peaks and the troughs of the CMB. So peaks appear less high, and the troughs appear higher if you have lensing. And so with this phenomenological parameter, this is not a physical parameter. This is just a phenomenological parameter, this lens parameter that we put in by hand to change the level of lensing that we have, for example, in this power spectrum. You have more and more smoothing if a lens grows to higher. And in the lambda CDM model, if you vary this parameter, this should be 1. It should be centered on 1. So this effect is measured at the 10 sigma level in Planck. But we measure, as I already told you already, the CMB lensing power spectrum also from the 4-point correlation function, because lensing leaves this non-Gaussian signal in the CMB maps. This allows you to measure lensing at the 40 sigma level, so it's a much more powerful measurement than what we get from the 2-point correlation function, which is shown in here. Now, what's the problem? Well, the problem is that this was supposed to be a consistency check. So we wanted to extend the lambda CDM model, allow this phenomenological parameter that has no physical meaning, really. It's not a physical model that tells you that you can just change the amplitude of lensing that you have. It was a consistency check. And it turned out to be slightly different than what we expected. So I know this is a busy slide. So what I'm showing you here, this is just the one-dimensional marginal distribution of this A lens parameter. In lambda CDM, you would expect this to measure this to be equal to unity. And if you measure this, for example, from temperature, which is this blue line here, this is 2.4 sigma higher than what you would expect. And this is consistent between the two likelihoods, so the two pipelines that we use, Planck and CamSpec, that's just names. This is consistent between different pipelines, and has been with us since 2013. So whatever we did to the data, this didn't change. We did tons of tests on this. Now, this would indicate that for some reason, the power spectra prefer more lensing than what you would predict in the lambda CDM model. Now, is this really lensing? Well, not really. And the reason is because we measure lensing. It's the same effect in the 4-point correlation function, and we don't see this excess. So it's more correct to say that there is an excess of smoothing in the power spectra at the level of a couple of sigma, which seems or looks like lensing. It's not lensing. And which could be just a statistical fluctuation. It might be that these peaks and troughs fluctuated in a way that we pick it up with this parameter. Now, why we worried so much about this? First, because we love worrying about 2 sigma stuff. Second of all, we were so bored about finding lambda CDM that, hey, okay, we have 2 sigma, we were gonna look at it. The second problem is that this is a phenomenological parameters, but you have extensions of lambda CDM that can give you more lensing. For example, the curvature of the universe, the dark energy equation of state, or even the sum of the neutrino mass can change the gravitational lensing that you see in your power spectra. And so if you have a CMB that the power spectra that prefer a higher level of CMB lensing, then you might have, and that's what we see, from CMB power spectra alone, you can have deviations in omega k or W. These are parameters that the CMB alone constrain very weakly, and so with large degeneracy bananas and so on, but still, that's why we worried about this. And the second thing is that we really hope that polarization could help, because this is essentially from temperature. And because polarization is sensitive to this parameter as well. But unfortunately, and this is something we struggled with for months, is that this parameter is degenerate with some of the systematics I told you about, in particular polarization efficiencies. And so depending on what exactly you do with these systematics, you can get deviations that are either 2.1 sigma when you combine temperature and polarization, or 2.8 sigma. When people tell you that the Allen's problem is 3 sigma, please don't listen, because this is not 3 sigma. We have an uncertainty, a systematic uncertainty, which brings you from 2 sigma to 3 sigma. So whether this is really a big problem or not, I think it's still uncertain. For all the tests that we could do, and I will show you one. Oh my God, it's already 50 minutes. Okay. Okay, so I will be short, but from all the tests that we've done, we haven't found a way to certainly assess that this is due to systematics. We did a lot of checks, and I'm going to tell you about one in particular. This is just to mention that even if you marginalize over these A-lens, you say, okay, this is, a way of picking up some systematic. This doesn't solve the H0 tension. So it goes from 4.2 sigma temperature plus polarization to 3.6 sigma when you marginalize over A-lens. It helps a little bit more for this S8 tension from 2.4 or 1.3, but again, this can still be a statistical fluctuation, so we don't know. But one test that we've done that I think it's very significant for this problem is that we see this A-lens deviation both at 143 gigahertz and 217 gigahertz. These are 2 of the frequencies that we use for the cosmological analysis. We can assess cosmological parameters from each of these frequencies separately. And this is relevant because each of the frequencies means different detectors across the focal plane. This means that if you see the same effect across detectors, it means that if it is a systematic, it's something that acts across the focal plane in the same way. And this is hard to do. If it's foregrounds, it's also hard because foregrounds have different amplitudes at different frequencies. And so it's not so easy to explain the same effect. There is one thing that we see that is frequency dependent, is this dip at 1450, which is larger in 217 than 143, and this might effectively be dust. But this changes if you cut this part. A-lens changes a little bit, but it doesn't solve this deviation all the way. Yeah, I will just mention what I was telling you about is that, so for example, this is curvature and omega m, and these are the Planck constraints, the colored ones. And you can see that we shift from flatness if we open up omega k, and this is due to the fact that negative omega k can actually give you a higher lensing in the power spectra. But the reason why we say, it's not that the universe is curved is that when we add BAOs, then we are back to flatness, to omega k. We get these very nice constraints that are centered around 0. And there is something very similar with WA and W0, the dark energy equation of state. Again, you see these huge bananas. The CMB is not very sensitive to this late time universe parameters. And again, if we combine with other data sets that are most sensitive to these parameters, we are back to lambda CDM. Whether this is some sign of things that we don't understand in the physics, whether it's statistical fluctuation, whether it's some systematic in the data, we don't know. I think just from this, you cannot claim there are systematics in the Planck data because we checked and we haven't found. You need to find evidence for, this being systematic. And so, for the moment, the best answer to this is it might be a statistical fluctuation, but future experiments will help us understanding this more. And I think I will just leave you with my conclusions that went really wrong. Oh my God. Well, then I will leave you with this.
future experiments, what exactly do you mean? Like, I haven't heard of any major mission to remeasure the CMB spectrum. Are you talking about nuclear or some?
No, I'm talking about CMB experiments. So it's true that from the satellite point of view, there is possibly a mission called Lightbird that might fly in 10 years, but it's really focused on large scales. But here in the US, there are these amazing ground-based experiments that are observing the sky, in particular polarization at small scales. So there is SPT in the South Pole, and there is ACT in Chile, and ACT in particular, Advanced ACT, have a program to observe large part of the sky, and this will be super useful because Planck is full sky, so our cosmic variance is very small, and therefore you need ground-based experiments that measures comparable F-sky in order to make meaningful comparisons.
Just curious what the final value of measure of non-Gaussianity is on Planck. I know you didn't get into it in this talk.
Yeah, I mean, depends on clearly what shape you're interested in. It's FNL is measured to be plus minus, I should know this number better, 5, right? Yeah, 5. But that's one particular kind of non-Gaussianity. You have all kinds of shape, and that's the level at which we are, yes.
Could interactive dark matter be also a good way to explain the tension between the H star?
Oh,
sorry.
What's that?
No, I was just going to ask that very same question.
Okay. So I've seen models of dark matter, dark energy, but I think those do not work very well. There were models, I think, from Julianus-Gurg et al. That were like looking at dark matter neutrinos. I think they can explain a part of these differences, but in any case, not all of the differences that we see. I would say, yeah, that's.
For the tension in the Hubble constant, can you explain that if you let the dark energy vary in some non-physical way?
Absolutely
it just
not.
turns itself off at redshift 2 or something?
Yeah, so people have tried that. The problem with that is that you want dark energy to do something weird when it dominates, so at redshifts, like lower than 1, for example. And so, you might imagine, okay, maybe dark energy at some point does something super crazy and accelerates the universe so that we measure today H not to be higher than what Planck predicts. The problem is that you have all these amazing BAO measurements and supernovae in the intermediate that, even if H naught comes from having absolute calibrations of either BAO or supernovae, but even without the calibration, these measurements tells you about the relative distances between these objects. And it tells you that dark energy didn't do something crazy. I mean, it tells you that there was no sharp transition of dark energy that happened at redshifts, where we have basically data till redshift of 2. That it must be something smooth, otherwise we would see big changes in the supernovae or in the BAO data. But yeah, absolutely, that's one of the first things that people have thought about.
So there is a dip in the TT power spectrum,
Yes.
low L around 20 and 30.
Yes.
Is EE data precise enough to say something about that?
At the level of accuracy at which our likelihood works at those L, no. But it doesn't exclude it. And also those L's for the E likelihood is so you were sorry, I was looking at yeah. So this dip here which also I got super excited for years. We're not the first to observe this. WMAP also observed it, so it's not in our data. It's in the sky. Two experiments have observed this. Yeah, so the corresponding, so at these scales, we have large error bars in EE, a lot of scatter. Some of this is due to systematics. So I would say that we need another experiment to measure better these scales. The pity is that, so we use these large scales in EE. You might have information from TE. The problem is that we don't use this data because we fail some null tests. It's super tricky to use this data because it's based on understanding systematics with end-to-end simulations, which are super costly. We have like 300 of them without me. We have 300 of them. We use them to build the likelihood for these and model the systematics. They were not enough to understand TE properly and how the uncertainties in the system in the foreground cleaning of the temperature maps. These were not included in the simulations. So there were a lot of tricky, unfortunately, and limiting factors for which we couldn't use this data, because potentially this would be the most useful check for this feature. I'm super excited by that feature, but unfortunately, that's the best we could do.
The full sky low polarization is still more work.
Yeah, I think Lightbird is going to be very exciting for that. Yes.
Oh, one last question.
So you seem quite sure that there's no one event that's pivotal in this, and yet there is a very important phase transition in the universe that your theory, I believe, still neglects, and that is the triple point of hydrogen at 13.8 occurs just when a redshift of 6 or so, just when we're assuming the universe reionizes. But what if it simply just freezes out all of its hydrogen and you misunderstood what happened?
So if you say that there is something tricky going on with reionization, basically, that's what you're saying.
I'm saying more likely there is something tricky going on with freezing out of hydrogen and changing the transparency of the universe. That's
at the epoch of recombination, I mean. So something weird going on in the way recombination happens. We tested that.
Not so much recombination, that was at Z equals 1,000. I'm talking about events at Z equals 6. Which is the
perfect. So reionization, the reionization history. As I said, so the CMB is not super sensitive to the details of how reionization worked, but we do see this bump here, okay? So something happened in the universe which looks like reionization, okay? This is, this is a clear sign of reionization. Then exactly how this evolved in time, we're not very sensitive to the details of that. And as I showed in this plot here, this really shows this. So this is the free electron fraction as a function of redshift. So in the baseline model, this just is the line. I mean, we assume that this goes like that, and when this happens is still our free parameter. But in this work, we really binned essentially these different amplitudes and let them vary. So this could potentially have done crazy stuff, and it doesn't. But the CMB is not very sensitive to the details of what happened and how exactly reionization happened.
Okay, well, let's thank Sylvia one last time. We'll be around on Friday.
I think, a result of the dimension of the collaboration. I mean, just for the likelihood, as I was saying, we had like 4 different